Welcome everybody to Algebra 2, Section 7.2, Graphing Rational Functions. Now, this is a big one out of Chapter 7. The inverse variations that we covered yesterday, yes, that's an important part to introduce these functions that take the form of fractions. But what the graphs of these functions look like and then how to solve, those are going to be the big topics of this chapter. So we're going to take some time, make sure we understand the process of graphing these, and then we're going to move through it right away. I think you're going to latch onto it pretty quickly. All right, so let's take a look. A rational function has the form where our f of x, the function itself, equals what looks like a fraction of two other functions. So our numerator is its own polynomial, and the denominator is its own polynomial as well. Okay, the inverse variation function, that's what we talked about yesterday in 7.1, it's the basic rational function, and it takes the form of y equals something over x. Okay, now the graph down below starts that off with an a value of 1, and this is where we can apply our parabolic charades. So if I kind of move these windows out of the way for you here, you can see that when we have that form of 1 over x, then essentially we get something where we can see horizontal shifts, vertical shifts, stretches and shrinks, and even vertical flips. So what we're going to do is we're going to jot down the parent function itself in a way that shows us where that a value, h value, k value that we're familiar with charades, where that stuff applies. So we're going to say y equals a over x minus h, and then a plus k outside the fraction. Okay, and just like before, the a value, it shows up in the numerator, but it's still a number that's multiplied into our fraction. That's going to show us vertical stretches and shrinks, and even a vertical flip if it's negative. The h is going to show us any shifting left or right, and the k value is going to show us any shifting up or down. So we get that same type of format that we saw with parabolic charades way back at the start of the year, even applying with these rational functions. Even though it looks a little different, it still behaves the same. All right, our process for graphing. I've broken this down into 4 steps, and this is how I go about teaching this. I think the more we can break down the processes in easy to understand terms, the better off we're going to be. Okay, so if we have some big function where the numerator is a polynomial, the denominator is a polynomial, the first thing we want to do is to factor anything and everything. Factor the numerator, factor the denominator as much as we can, because sometimes we'll get factors to cancel, and those canceling points, those factors that do cancel, they produce what we call a hole in the graph. The graph will just have a little gap in it at that point. So after it's factored, we go through what I call the 3 zeros. That's our next step. We're going to set the numerator equal to 0, and if it's already factored, that's easy. That'll give us the x-intercepts. We set the denominator equal to 0. Whenever we're dividing by 0, that's like an undefined slope. We get a vertical asymptote. And again, if it's already factored, that's really easy. And then letter C, we're going to simplify what happens when we plug in x equals 0. Well, that gives us the y-intercept. That happens whenever x equals 0. So right away, we were able to get a vertical asymptote or more than one vertical asymptote. And we're also able to get x and y intercepts. We're getting points on the graph. We're making the picture after the first step, which is really nice. Secondly, I call this one the big X test. What happens when x is huge? And we're going to be looking at degree. So the first option is the denominator takes over. It has a higher degree. That makes a horizontal asymptote of y equals 0. And the reason being, if the denominator has a higher degree, that means that it's going to grow faster than the numerator will if x is huge. So let's make a little example off to the side. You don't have to copy this down, but just to explain the big X test. If we have the function, let's say like 2x squared plus 4x plus 7 all over 4x cubed minus 2x squared plus 2x, something like that. When x is a huge, huge, huge number, say like 500,000, the x squared is going to take over the numerator, and the x to the third is going to take over the denominator. Those have the biggest powers. They take over those polynomials in the top and bottom. So really, when we look at the fraction, we're not really concerned about the other stuff. It's going to be washed out by those leading terms, the ones with the highest degree. Well, if the denominator is taking over, think about what happens if a fraction has the denominator take over. This x to the third power in our denominator is going to take over that x squared. It's just more powerful. It's got a higher degree. So if that's the case, think about a fraction where the denominator is increasing. So if we have 1/2, then 1/8, then 1/50th, then 1 over 10,000, those numbers are getting tiny, tiny, tiny. So they're getting drawn closer and closer to a horizontal asymptote of y equals 0, a height of 0. 1 over 10,000 is a tiny number. It's really close to 0. That's why that takeover produces a horizontal asymptote when the denominator takes over, I should say. Now, what about if they have equal degree? Well, let's say after we look at what's taking over the numerator and denominator, we have like 4x to the 5th over 3x to the 5th. Well, if those have the same amount of power, no polynomial takes over the fraction, then they effectively equal each other out. So they, again, this isn't making algebraic sense, but effectively what happens is since they have equal power, we look at the coefficients. And the fraction that's made, in this case 4/3, is where our asymptote will be. Since they have equal power, we look at their leading coefficients and make a fraction out of it. Okay, and it'll still be a horizontal asymptote where y equals that fraction. And lastly, letter C for our big X test. If the numerator takes over, well, that means we've got something other than a horizontal asymptote. It could be maybe a line that's going with some slope, or it could be an asymptote of a totally different nature. All right, after all that is done, we'll have vertical, horizontal asymptotes in place. We'll have some points on the graph from our intercepts. If that's still not enough to tell what the graph is doing, we resort to step 4, which is, I just call it freshman graphing. We're going to make a small table of values, maybe use the calculator, but that takes some time. But we're just going to plug in some values that are close to vertical asymptotes to plot some points nearby to help fill in the gaps. All right. I apologize, I did spend a lot of time talking about that, but if we understand those steps, we are going to have an easy go at this. So our first example, compare the function with the parent function 1 over x. All right, so here's where we're using our charades language. So in number 6, g of x is -9 over x. Well, that negative out front is telling me that it's a vertical flip, and the a value of 9 tells me that they multiplied that fraction by 9, so it is 9 times as tall. All right, for number 10, that 0.1 in the top as a fraction, that would be 1/10. So my a value is a number smaller than 1. That tells me it's 1/10 as tall. And that's the only thing that's being changed about that rational function. Okay, so that's the first type of problem we're going to encounter, just simply comparing graphs. All right, the remainder of our examples are going to be practicing those steps in order to answer all these questions about rational functions. So we're going to go right through it. For letter A, step 1, is there any factoring to do? Factoring and simplifying. And in this case, no, there is not. We've got 1 over x plus 2, very, very basic ground level rational function. So there's no factoring or simplifying. We can jump right into our 3 zeros. Okay, when my numerator equals 0, that's going to tell me any x-intercepts that I have. And you can see 1 equals 0. Well, that's not a true statement. That tells me there's no x-intercept. Now, that's kind of a bummer. It would have been nice to put some points on the graph. The next one, what happens when my denominator equals 0? Denominator is x plus 2. When I set that equal to 0, it says x equals -2. That's the equation of my vertical asymptote. So I'm going to draw in that vertical line, x equals -2. And then lastly, when x equals 0, I'm left with y equals 1 over 0 plus 2. Y equals 1/2. Okay, that's my y-intercept, the point, 0, 1/2. So I'll go ahead and plot that on the graph right there. So you can see we're kind of building this from the ground up, and we've already got some nice structural components there that'll help us build this. Next, our big X test. Our big X test, well, looking at this, the denominator has a degree of 1. I'm just going to jot that down off to the side. You know, once we get a feel for what to look for, we don't have to take the time to do that. But for the notes, we want to know how we are figuring out what's taking over. And the numerator has no x terms in it. The numerator has degree 0. So since the denominator takes over, I'm just going to put den take over. I know my horizontal asymptote is y equals 0. We can go ahead and add that to our graph. All right. Well, right away, I can tell, based on where my y-intercept is, I know that that graph is going to be drawn toward the vertical asymptote as I move to the left, and toward the horizontal asymptote as I move to the right. So I've got half of that graph pretty much established. The last thing I need to do a little bit of freshman graphing. Okay. And really here, I only need one more point. The table doesn't have to be really excessive. I'm going to pick one that's close to my vertical asymptote, and it would be nice to choose an x value over here to the left, because I already know what the graph is doing to the right of that vertical asymptote. Let's try when x equals -3. Well, if x equals -3, I'm going to plug that into the very beginning here, since I couldn't simplify it at all. If I plug in a -3, I get 1 over -1. So my y value there is -1, and now I have that point on the graph where I can extend the graph being drawn towards those asymptotes in either direction. There's our graph. Let's just double check that we've accounted for everything. Since there was no simplifying, there is no hole in the graph. Okay, so we've got the holes accounted for. There's no x-intercept. We got our vertical asymptote, horizontal asymptote. There's a y-intercept there. Last thing we need to do is domain and range. Domain and range, here I'm going to show you a fast way to describe this. It's called set builder notation, and it's a fast way of saying all x's except for. Because if we scan this graph from left to right and look at all the x values that lead to the graph, everything works except right here where we had our vertical asymptote. So I'm going to say all x's such that x does not equal -2. That bar is read as such that. So my domain is all x values as long as x is not equal to -2. Okay, and then for the range, now I'm looking at the y values, the heights, and they work just fine. Everywhere along the y-axis, I'm leading toward the graph except for when y equals 0, where I had my horizontal asymptote. So I'm going to do a similar statement here with the y values, saying my range is all y values such that y does not equal 0. Every other y value is okay, just y equals 0. That's what we have to leave out. Okay, so there's our basic process, and you can see it keeps everything nice and organized. We build the graph as we go through it. Very procedural approach. We take the time to understand it now. It's going to be much easier when we start to pick up the patterns. All right, for letter B, same prompt. Well, let's see if we can't simplify this first. So x minus 2, my numerator is already factored, but the denominator, oh, I can take out a greatest common factor of 3, and then I can factor the difference of squares that's left to 3 times x minus 2 times x plus 2. So this fraction is really the quantity x minus 2 over 3 times x minus 2 times x plus 2. Oh, and we get a factor that cancels out. So I can simplify this, and I'm just going to sneak over here where there's some room. The function is really y equals a 1 for a placeholder in the numerator over 3 times x plus 2. And that's going to be really helpful to have a simpler function if we have to resort to freshman graphing. Now, what this does tell me, when I factored and simplified, there is a hole at x equals 2. That is the point 2 comma something. How did I get that 2? Well, I just took the solution that came out of that factor that canceled. If x were to equal 2, and if we could try plugging it back in, we'd get 0 over 0. So the graph can't be computed at that point. Well, this x value of 2, if I plug that back into my simplified function up there, I got 1 over 3 times 4. That's 1/12. Okay, so there's our hole in the graph. And now that we've got this simplified function, let's go ahead and get to work. So first thing are 3 zeros. Okay, when the numerator equals 0, well, looking at my simplified function, I've got 1 equals 0. Again, that's telling me no x-intercepts. When my denominator equals 0, well, that's 3 times x plus 2 equals 0. I divide away the 3, solve that factor that's left. I find that x equals -2 is our vertical asymptote. Oh, that kind of worked out just like the last time. So we'll sketch that in. And then lastly, when x equals 0, I get 1 over 3 times 0 plus 2. Oh, that's y equals 1 over 6. So that means that my y-intercept is the point 0, 1, 6. Plot that point there. 3 zeros, done. Next, the big X test. Well, if I look at my big X test here, I'm going to go ahead and add some bullet points back over here. With the simplified function, you can see that the numerator has degree 0. There's no x's left there. And the denominator has degree 1. There's only one x factor there. And we could even use the original, maybe so we can see the powers there before it was all factored out. We would still see that the denominator takes over. And again, that's telling me the horizontal asymptote is y equals 0. Let's sketch that in. All right, building our graph one little bit at a time. Okay, we can already tell what's happening over here on the left. Right, it's going through that y-intercept being drawn toward the asymptotes. I just need to be careful that there was a hole in the graph when x equals 2, so I want to be sure and put an open circle there to show that there is in fact a hole in the graph there. And again, I don't know what's happening on the left-hand side of that vertical asymptote, so I'm going to have to do a small amount of freshman graphing here. If I plug in an x value of -3 just to the left of that asymptote, plug that into our simpler equation, I get 1 over 3 times -1. So I get -1/3. And we'll go ahead and plot that in right there. We can connect it to its asymptotes. And we have our graph. Domain and range. Last thing we need. My domain is all x values except for, well, now I need to look out for that vertical asymptote, so x cannot equal -2. And I can't plug in the x value of 2. There was a hole in the graph there, so x can also not equal +2. For the range, it's the same thing, but now with the y's. Well, all y values, as long as y does not equal 0 for that horizontal asymptote, or doesn't equal that 1/12 that came up when I had the hole in the graph. Everything else is covered. If I were to describe this work, it's not difficult, it's just tedious. But as long as we follow our steps, really, we know exactly what we should be looking for next. And really, we're building the graph the whole way, so it never feels like we're doing work for nothing. All contributing to the greater good. All right, letter C. Here, let's factor and simplify. Can't factor the numerator. That's just a constant, but the denominator is a difference of squares. Okay, so we'll factor that out. That's going to make it a lot easier to figure out where the denominator is 0 and so forth. Okay, so I figure out, since no factors canceled, there are no holes in the graph, which is always good. That makes domain and range easier. Let's move into our 3 zeros. If the numerator were to equal 0, well, I'd get this equation, -3 equals 0. No x-intercept. Okay, and we haven't had one of those yet. If I set the denominator equal to 0, I get these factors set equal to 0, and since it's already factored, it's easy to tell that x equals 2 and x equals negative 2. Now I have two vertical asymptotes. That is okay. That can happen. Go ahead and plot both of those. And lastly, what happens if x were to equal 0? Well, then I would have negative 3 over negative 4. So my y-intercept is the point 0, 3/4. Go ahead and plot that in there. Big X test. This one's a no-brainer. Looking at our original function, we've got a degree of 0 in the numerator and a degree of 2 in the denominator. So that denominator takes this function over. That means my horizontal asymptote is y equals 0. And I know we've seen a few examples where that is the case, but it won't always be the case. And I'm sure we have examples coming up where that changes, just so we don't try and think that that's a theme here. All right? And I'm going to have to do some freshman graphing here. You can see now we've got the vertical asymptotes make 3 slices of our graph vertically. And in the middle, we have middle slices here, weird things can happen. So you've probably been taught that a graph cannot cross an asymptote. Well, that is simply untrue. Especially in a middle slice like that where we've got multiple vertical asymptotes happening, we could see weird things happen in the middle. Sometimes with the asymptotes, you will see like a mini parabola happen inside. Sometimes you'll see like a weird cubic thing happening. So we need to find some points inside as well as outside of those vertical asymptotes. But it's still not a difficult table to make. I'm just going to choose negative 3, negative 1, positive 1, and positive 3. Okay, so what happens when I plug those in? Well, if I plug in a negative 3, okay, and I'm going to choose the original because then I only have to plug x into one place, but I could use the simplified one as well. If I plug in a negative 3, then I'm going to get negative 3 over 9 minus 4. I'm going to get negative 3/5. So at negative 3, down here at negative 3/5, okay, I know what this branch or this portion of my graph is doing. It gets drawn towards the asymptotes away from there. Likewise, if I plug in a positive 3, I'm going to get the same result. Right, it'll be negative 3 over 9 minus 4 again. So I get that same value, and my graph starts to take on a little bit of symmetry here. What about negative 1? Then I would have negative 3 over 1 minus 4. Oh, that's negative 3 over negative 3. It's a positive 1. Negative 1, positive 1 is another point on that graph. And if I plug in positive 1, I will get the same result. So the point 1, 1 is on that graph as well. So we can see that we definitely have one of those mini parabola cases here. There's our graph. Domain and range, and we're done. My domain is all x values as long as x does not equal plus or minus 2. Those are where the vertical asymptotes were happening. And the range, I can accept any y value as long as y is not equal to 0. And here's where you'd really want to be careful, because if we were to have that cubic case in the middle, then we would have a y value of 0. So we'd have to say that our range is all real numbers. So it's important that we know what's happening when we see that weird middle slice happen. It's not very common, but when it does, it just requires a little extra work. A little extra work. All right, letter D. Okay, here we've got some factoring that we can do. Let's take a look and see what happens. In my numerator, let's switch to the black marker here. In the numerator, I can take a GCF of x out. In the denominator, I can take a GCF of 3 out. And none of those factors cancel. All right, well, so we know there are no holes in the graph. Good. Let's move into our tests. First of all, 3 zeros. If I set the numerator equal to 0, that's going to give me x-intercepts. Well, here I actually have a function up there. I find that I get x-intercepts at the point 0, 0, and at the point 1, 0. And again, those x values are coming out of solving each factor. Let's plot those points, 0, 0, and 1, 0. It's kind of weird that they're so close together, but hey, the math checks out. Next, what happens when the denominator equals 0? Well, that would be 3 times x minus 2 equaling 0. If I solve that factor, I get a vertical asymptote of x equals positive 2. Okay, so we'll go over to x equals positive 2. There's that vertical asymptote. Right. And lastly, what happens when x itself is equal to 0? Well, then I get y equals 0 over negative 6. So that tells me that my y-intercept is the point 0, 0, which makes sense because when we found that as an x-intercept, it's also on the y-axis. So no real surprises there. Next, for the big X test. Well, here the numerator has degree 2, and the denominator has degree 1, so the numerator takes over. That means there is no horizontal asymptote. Huh. Well, that's not the end of the world. We may just have some weird asymptote. We might have to plot a couple extra points in our freshman graphing to see what that graph is doing off to the ends, but no big deal. Freshman graphing. Now, I kind of have an idea based on these points that I know it's getting drawn towards this vertical asymptote, and I'm imagining it going this way, but I guess it could go downward. I need to see what some other points are doing. So I'm going to take away that green line. That I should not have put that in there so quickly. All right, so let's choose an x value of 1/2, or sorry, not 1/2, 1 1/2, or 3/2. And we'll also choose one that's further off to the left, say like -3. And we need one on the right-hand side of that vertical asymptote. Maybe a couple of those, actually. Let's do +3 and extend it over here too. +4 and +5. I just want to get a good idea, so I'll plug in some points. In this one where I need so many points, it might be worth my time to type this into the calculator and use its table of values. All right, if I plug in a 3/2, well, then let's see. I would have 3/2 times 1/2 over 3 times 3/2 minus 2 is -1/2. Okay, so that would be 3/4 over -3/2. And 3's will cancel. And I'm going to get -1/2. Right, I believe so. Oh boy, let me double check that with the calculator. I'm pretty confident in that math, but for the video I want to be positive, so let's check. I've got 3/2 squared minus 3/2. Divide that by 3 times 3/2 is 9/2 minus 6. And I get -1/2. So yes, I was correct. I just wanted to double check. All right, so -1/2 right here. So that's showing me that I was wrong before. This graph is actually bending down towards this vertical asymptote. Okay, at -3, here I'm going to have 9 minus -3. Okay, that's 12 over 3 times -3, -9 minus 6, -15. All right, so -12/15, that's almost -1 out here at -3, like that. Okay, so it looks like my graph is kind of bending this way. +3, 9 minus 3 is 6, over 9 minus 6 is 3, so I got the point 3, 2. Okay, if I look at 4, 16 minus 4 is 12, over 12 minus 6 is 6, and another height of 2. And that's not really surprising. We had that kind of symmetry with points close together on the left. Let's see what happens when we plug in a 5. 25 minus 5 is 20, over 15 minus 6 is 9. Okay, 20 over 9, that's just a little bit over 2. About right there. So it looks like what I'm seeing is something like this. All right, and if you're wondering, well, it looks like we got a horizontal asymptote happening somewhere in there. Well, you're kind of right. If we wanted to figure out what was actually happening, we learned a long time ago that we can actually do this division that our function is telling us. So we could do x squared minus x divided by 3x minus 6 and use long division. That would give us the equation of this asymptote that is kind of slanting through there. All right, so if you wanted to figure it out, that's the way to do it. For our domain, here we've got all x values except for that vertical asymptote at 2. And for our range, well, we've got all y values as long as y is outside of this region. That's the only place height-wise where the graph is not seen from the y-axis. So we may have to turn to a calculator to find those minimum and maximum points to find the values in between. And actually, I'm just going to take a second and do that. I know this is becoming a long video, but it's a 2-day lesson. All right, when I type this into the calculator and actually look at the graph, we actually did a pretty nice job with our freshman graphing. And I'm just going to real quickly do a calculate maximum. And that gives me a maximum height of y equaling 0.057 right here. So my y values, as long as y is less than or equal to that 0.57, or the y value is greater than or equal to whatever this height is here, we'll have all those values in our range covered. So let's do a calc min. And I get 1.94. As long as our y value is not in between those those y values, we'll be okay. It has to be either below 0.57 or above 1.94. So pretty complicated when we have no horizontal asymptote. That's not going to be a huge focus this year in Algebra 2, but boy, will you cover it in pre-calc next year. So it's nice to have a look at it right now. And our final example, graph this function. Oh boy, it looks like a monster, but it's really not that bad. What we want to do is factor. And this is a prime candidate for how factoring can greatly simplify these problems. So in the numerator, I can take a GCF of 3 out. Oh, and then I'm left with a nice trinomial that factors to x plus 3, x plus 1. Okay, so I want to hang on to that original just for my big X test. It makes it a little bit easier. And in the denominator, that's a nice trinomial. I've got x plus 2, x plus 3. Oh, okay. So my function is really 3 times x plus 3 times x plus 1 over x plus 2 times x plus 3. I get a factor to cancel. My function simplifies to y equals 3 times x plus 1 all over x plus 2. Very nice. I did find that there's a hole in the graph. And that occurred when, let's see, x equals, what's the solution that comes out of that canceled factor? When x equaled -3. -3 comma something, let's plug that back into our simplified function up there. 3 times, it would be -2, that's -6 over -1. So +6. -3, +6 is going to be a hole in that graph. Okay, let's move into our 3 zeros. If I set the numerator equal to 0, I will find an x-intercept when x equals -1. Okay, let's plot that point. If I set the denominator equal to 0, I will find a vertical asymptote when x equals -2. And we've seen a lot of -2 vertical asymptotes. And if I set x equal to 0, I find that y equals 9/6. So my y-intercept is the point 0 3/2 when I simplify that fraction. So up here at 1.5. Big X test. Here's where looking at the original function is very helpful because we have those powers. What's taking over the numerator is that degree of 2, that 3x squared. What's taking over the denominator also has a degree of 2. It's a 1x squared. So my horizontal asymptote, they have the same degree. There's no clear takeover. The horizontal asymptote is y equals, let's look at those leading terms, 3x squared over 1x squared, 3/1. So y equals 3 is my horizontal asymptote. All right, and before we go to freshman graphing, look at the x and y intercepts just falling in line nicely with what that graph should do as far as being drawn toward the asymptotes. Once again, I do need to see what's happening to the left of that vertical asymptote. So for my freshman graphing, I'm just going to test -3. And let's use our simplified function for that. 3 times, oh, we can't test -3. We said there was a hole in the graph there. Let's do -4. 3 times what would be -3, that's -9, over -4 plus 2, -2. So at -4, positive 9/2, we have another point in the graph, and we can tell that the graph is going to behave like so. We know there's that hole in the graph, so we show that with an open circle and have the graph continue on its way being drawn toward the asymptotes. Domain and range, and we're done. My domain works as long as I have x values that are not equal to where my vertical asymptote is and where that hole in the graph was. For the range, I can accept any y value as long as it's not on that horizontal asymptote at +3 or the height of that hole in the graph, which was 6. So there you have it. This really could be considered a pre-calculus lesson. But I think that, at least for the most part, we should be able to meander our way through these problems, handle those steps, and really, if you understand this, you are set. I understand it's a lot of work. I understand it's a lot of writing and everything, but hopefully we could see how all of this ties together. I mean, look at all that we talked about. We talked about degrees. We revisited factoring. We revisited intercepts. We haven't talked about those in quite a while. Domain and range, those come back into play. So really a lot of work with functions that we haven't seen in a while. It all ties in nicely with just this idea of a function that takes the form of a fraction. So I thank you for your patience. I know this was a long video, but I cannot stress enough that we have covered everything you might encounter when it comes to graphing rational functions. So if you are able to understand this material really well, you are well prepared for future math. So that does it for our big 7.2 lesson on graphing rational functions.